Welcome to the second part of our series on electrical diagnosis and repair. In the previous video, we looked at how to use the wiring diagrams in the repair manuals as a roadmap to troubleshoot electrical problems. And we looked at the use of a digital multimeter to troubleshoot problems using tests for voltage drop and continuity. In this video, we'll look at some additional tests using the digital multimeter that can help you isolate problems. And we'll look at some other tools that can make electrical diagnosis easier. We'll conclude with a look at the proper ways to repair electrical terminals and harnesses once you've isolated the problem. After viewing this video, you should be able to use a digital multimeter to do a parasitic draw test. Use a digital multimeter to test a switch. Use a test lamp to check for current flow. Describe the proper procedures to repair a wiring harness, and describe different measures of wire sizes. Current is the flow of electrons through a conductor. The ammeter function of the digital multimeter is used to measure current. When unwanted current is flowing through a circuit when the ignition switch is in the off position, that current flow is called a parasitic draw. Parasitic draws can, over time, result in a battery that runs down as the stored voltage is used. There are several devices that normally use current when the ignition key is off. Most of these devices are electronic devices that use the current to retain the memory in an electronic control unit or that power vehicle security systems. On a typical vehicle, the sum total of current draw is less than 100 milliamps, or 1/10 of an amp, with many of the vehicles having a draw of less than 50 milliamps. There are several causes of an excessive parasitic draw, but the most common is a light not being turned off, such as a glove compartment light, an underhood lamp, or a rear compartment lamp. The most reliable test to use to isolate the cause of a parasitic draw is with the ammeter. Since an ammeter must always be used in series with an electrical circuit, an inductive probe will save you time because it allows you to make your tests without opening the circuit. If your meter doesn't have one, then you'll have to disconnect the negative battery cable to put the meter in series. There are a few precautions that must be followed prior to doing a parasitic draw test with an ammeter. Most digital multimeters are protected by a 10-amp fuse to prevent overloading the meter. Typical parasitic draws are less than 5 amps. Prior to installing the ammeter, make sure the power to the circuit is off before cutting, unsoldering, or disconnecting the circuit, as even small amounts of current can be dangerous. Never attempt a current measurement where the voltage is above 600 volts. If the meter fuse blows, you can be injured and the meter will be damaged. Never attempt to do a current draw test on a lead-acid battery that has recently been recharged. And never crank the engine or operate accessories that draw more than 10 amps when doing the test, or the fuse may blow and the meter can be damaged. To do the parasitic draw test, set the rotary dial on the meter to the milliamps-amps direct current function. Insert the probes into the correct ports. Then disconnect the negative battery cable from the battery. Many onboard computer systems will take several minutes to either shut off or to go into a sleep mode, so you'll have to wait until this happens before conducting the test. You can use this time to disconnect the underhood lamp, if the vehicle has one, by removing the bulb, disconnecting the connector, or by pulling the fuse for the circuit. Once the onboard computers have shut down, you're ready to do the test. Touch the black probe to the negative battery terminal, and then touch the red probe to the battery cable end. On most vehicles, the current draw shown on the meter display should be less than 0.050 amps, or 50 milliamps. Always check with the repair manual, as a draw of up to 100 milliamps can be considered normal on some vehicles. If a high current draw is present, you can isolate the circuit causing the draw by removing the fuse for each of the circuits until the current reading on the ammeter drops. Once the circuit is isolated, test the components and their connectors to determine the cause of the fault. Then repair and recheck your work by reinstalling the fuse and measuring the current draw. As we saw in the first part of this video, testing a circuit for continuity to ground is a good way to confirm a shorted circuit. Beyond testing for shorts, continuity test can be used to check for open circuits and switches. Let's look at an example on a vehicle with inoperative brake lamps. The typical stop lamp switch is a normally open switch. That means that when the brake pedal is at rest, the switch plunger is pushed in and the circuit is open. No current flows through the switch to the rear brake lamps. As the brake pedal is depressed, the plunger extends by spring pressure to close a set of contacts inside the switch. The contacts close the circuit and allow current to flow to the tail lamps and the center high mounted stop lamp where the brake lamps are illuminated. To test the operation of the switch, set the digital multimeter's rotary dial to the ohms function to test continuity through the switch and insert the probes in the correct ports on the meter. Many multimeters have an audible alert that beeps when there is no continuity. With the ignition switch in the off position, connect the probes to each side of the stoplight switch. Then depress the brake pedal and listen for the beeper. A continuous tone confirms that you have continuity. If there is no tone, there is no continuity and the switch is open when it should be closed. The beeper method is convenient because you don't have to look at the display when doing the test. If your meter doesn't have a beeper, then look at the display. With the brake pedal unapplied, the reading should be OL, or over limits, indicating an open circuit in the stop lamp switch. When the brake pedal is depressed, the meter should show 0 ohms resistance, meaning there is continuity through the switch. If the meter continues to read OL, check your connections at the switch and retest. If the meter connections are good, then you've confirmed the switch is open, and replacing the switch should solve the problem. Replace the switch and have an assistant confirm that the brake lamps work when the pedal is depressed. We just saw how the beeper function of a digital multimeter can be handy in confirming continuity. This function is particularly helpful in testing connections for intermittent open conditions. To check a connector for an intermittent open, set up the meter as you did for the stop lamp switch test. Press the alert button to set the audible tone, then insert the probes on the opposite sides of the same connector terminals. There should be a continuous tone from the meter indicating continuity. Then do a wiggle test on the connector and listen for the tone to stop. If the tone stops, that means the connector is loose and open circuiting as the connector is pulled on or through vibration. The connector should be separated and cleaned or repaired as necessary. Test lamps are an easy way to test a circuit for the presence of current. A big word of caution before we look at the tests you can do with a test lamp. Never, and we mean never, use a test light on any part of a circuit that leads to an electronic control unit or on a supplemental restraint system airbag. Self-powered test lamps send an electrical current through the circuit that can cause the sensitive circuits in an electronic control unit to melt, or they can cause airbags to deploy. While the non-powered test lamp creates a short to ground in the circuit and allows current to flow through the test lamp to ground. A non-powered test light consists of a pointed probe, a 12-volt light bulb, and a flexible ground lead. Non-powered test lamps are used to check for the presence of voltage in a circuit. When the bulb in the test light is lit, it indicates that voltage is present. A non-powered test lamp can be used with confidence on any non-computer controlled circuit. Let's look at an example. Self-powered test lights are also known as continuity lights. They are used to check the continuity of an open circuit. Self-powered test lamps look similar to non-powered test lamps, but they have a small internal battery attached between a light bulb and two leads. With a self-powered test light, if the two leads are touched together or connected through a low-resistance circuit, the bulb will light because doing so completes a circuit between the bulb and the test light's internal battery. We can't overemphasize this point. Never, and we mean never, use a test light on any part of a circuit that leads to an electronic control unit or on a supplemental restraint system airbag. The use of this test can cause the sensitive circuits in an electronic control unit to melt, or they can cause airbags to deploy. Serious personal injury can result from ignoring these cautions. Because of their concern for your safety, all manufacturers strongly recommend that you never use a self-powered test lamp on today's vehicles. As we've already seen, there are safer and better ways to test for continuity. The digital storage oscilloscope is rapidly finding its way into most technicians' toolboxes. This extremely flexible tool is used to diagnose electrical and electronic systems by displaying the waveforms of the monitored circuits. There are two basic waveforms for electrical activity. An alternating current waveform is displayed as a sine wave. A sine wave starts at 0, then goes up to positive, back down through 0, and then to negative and back again to 0. The number of cycles per second is the frequency of the signal. A digital voltage signal is a signal that is either high, representing on, or low, representing off. As voltage is turned on in a circuit, the waveform line increases to the specified voltage and remains constant until the voltage is switched off. The amount of time that the voltage signal is on is known as the pulse width. Direct current is a waveform that appears to be a straight line across the screen at a specified voltage. Any changes in voltage will raise or lower the position of the line across the screen. For basic electrical diagnosis, you can use the oscilloscope storage feature to test for intermittent conditions. The leads on a digital oscilloscope function the same way as those of a digital multimeter, although most oscilloscopes have separate wiring harnesses for the probes that attach to one port. The benefit of an oscilloscope is that it has a memory that can track a voltage signal over time. If you suspected a poor connector, you can probe the mating terminals with the leads of the oscilloscope. Then turn the ignition key to the on position. The voltage through the connector will show as a straight line on the grid of the oscilloscope. Following the instructions that come with the oscilloscope, set the time divisions to capture the voltage signal over time. Then wiggle the connector. You might not be able to see the loss of continuity because it happens too fast, but the oscilloscope will detect a break in continuity of as little as 1 millisecond. You can confirm the results of your test by the playback feature, which allows you to check the signal for the entire time the test was conducted. A break in continuity will show up as a sharp drop in the intensity of the voltage line from the regular voltage down to either a lower voltage or to 0. The connector will have to be separated and cleaned or repaired as necessary. So far, we've looked at many effective ways to diagnose and isolate the causes of problems in an electrical circuit. Our diagnosis may lead us to a component, such as a motor or a switch, that can be replaced. More often than not, the problems will lie in the connectors, or to damaged or broken wires or grounds. For a load to operate properly as designed, the wire size used in primary automotive electrical circuits must not only handle the necessary current, but also any vibration and heat exposure. Wire sizes are standardized according to their diameter. The higher the gauge of a wire, the thinner the wire is. Most of the wiring used in automotive systems varies from 12 gauge to 18 gauge. The gauge of the wire has a direct effect on current flow. Lower gauge wires have less resistance to current flow as they provide a wider path. Thinner wires have a greater resistance to current flow than a thicker wire. When replacing a section of wire, it is imperative that you always use the same gauge wire in the repair. Think of Ohm's law. If you use a larger wire in the repair, the resistance of the circuit will be lowered and a higher than normal current flow will result. Using a thinner wire will increase circuit resistance and reduce current flow. In this video, we look at the use of the digital multimeter to test for current draws and continuity. Then we looked at other diagnostic tools that can help you isolate the causes of electrical circuit faults. Thanks for watching.